I want to talk about what we're going to do today. What we're going to do today is we're going to look at something called separable differential equations. And we've looked at this idea of differential equations. And if it's been a while since we've looked at it, just think back to what these represent. What they represent is they represent a few different things. A differential equation is any equation with really a derivative in it, right? And we said that you can have first, second, and so on derivatives. We call these first order ones when there's only the first derivative in them, right, naturally. Before we looked at this idea of a slope field, think about what these represent. These represent all the possible solutions to a differential equation, right? And a differential equation can be solved not in the traditional sense of finding x or y, because now you actually have two variables. It's just finding out what the actual function is that solves that. And we looked at one method of solving, which was integration, right? And if you use that antiderivative process, you remember there's a constant. And so that's what this kind of represents. It represents all the possible curves that are there, okay? But obviously, I mean, if I wanted to find just one solution, okay, how do I use that? Well, if you think about integration, in order to find a particular solution, what do you actually need in order to find one answer for the function if you're using integration? You need a bit more information. What information did I have to give you?
Point.
Yeah, point. Yeah, a point or some values. Yeah, some other kind of information about that. That's exactly what this is going to be about. And not only are we going to find the equation for that, we're also going to find the graph for that. And you can see how it matches up with this kind of situation here. I'll park that for now. Okay. So what I'm going to do is I'm going to talk you through the steps of solving a differential equation. So remember, it's of this form, but let me give you an example of the one we're going to do. Here's one we're going to do here. So as you're writing that down, let's have a chat about how we can approach this question. So remember, to solve a differential equation, what's it actually involving? To solve this means that I need to have an expression for y at the end. I'm looking for that, right? And you can immediately see the problem of what's happening here. Right? At this point in time, there are actually two variables here. And in terms of integration, we're used to seeing something as, you know, dy dx is equal to something, and then it's in terms of x, so we can just go ahead and integrate. This doesn't actually allow us to do that. Okay, this is why we classify this as a different type of differential equation with a different approach. All right, if we have two functions multiplied by each other in terms of x and y, this is when we classify it as separable. Right? And you can see that there's your x, negative 2x there, and e to the y there is your y component, right? So how are we going to approach something like this? Well, the name kind of gives away a little bit of the strategy that's there. Yeah, well, how are we going to separate them in some sense? And how is that going to help us solve this, right? Well, think about your normal method of solving a differential equation that was just integration, right? We want to sort of create a situation that allows us to integrate this. But we want to integrate them separately. We want to integrate the x's with dx and the y's with dy. And so that, again, is a bit of a clue of what's going on. So the first thing that we do, step one, is we treat, now this is very like kind of off-the-cuff mathematics, because we shouldn't really be doing this, but we treat dy dx as a fraction. Right, that's the first thing that we do. And then what we do with that is we group. Because when you think about your integration, you want to have dx with, you know, your x variables and dy with your y variables. So we group f of x with dx, and you group g of y with dy. All right. So what that's going to look like over here is if I've got dy dx is equal to negative 2x e to the y, right? I'm going to try and rearrange this algebraically so that I have the two together. Typically that means multiplying both sides by dx. And then the e to the y, well, I can divide both sides by that particular expression over here to bring that to the other side, like this. So I guess 1 on e to the y if you want. Okay? And so now we're going to integrate both sides separately because we have that situation that we wanted. There is a step 4, and this only occurs in certain situations. Step 4 is if you need to have a particular solution, we can substitute in the initial conditions. And that's only if they ask you to do that, right? All right, so let's go ahead and do this. So if I'm integrating something like this, typically I want to have this written as in index notation. So I've got e to the negative y here. Okay. And then so step 3, we want to integrate both sides separately. So let's go ahead and do that. When we integrate this, James, what are we going to end up with? So which side is easier for you?
I mean, the minus 2x is easier.
Yeah, let's do the right hand side then. What do you get?
Minus x squared.
Minus x squared over here. That looks good. Right and left hand side, Matt, what do you get when you integrate that? If I integrate the left hand side, what do I end up with?
Usually drop the, what do you drop? Integrate, it's the opposite, so divide by it.
Yeah, that's it. So you divide by -1, becomes negative e to the negative y, I suppose, right? Now at this point you may be wondering, oh, okay, what about your constants? Do you remember what I said about constants when we're applying two integrals here? Well, think about like what you would typically do. Here, when you integrate, what would you get? You get the function as well as a c, a constant, and same thing over here, right? So I've kind of sort of teased this idea of, oh yeah, you could do this plus c1 plus c2 because there's two constants. But typically the convention is, well, because we're just going to get two constants, we could just put them together as one constant, right? So we would have plus c like that. Yep, okay. So that's why we have a situation like this. We have our expression here now with a constant. Now, I suppose strictly speaking, this is the solution. It's the general equation to the differential equation, right? But kind of like when you're solving equations, it's really not solved until you have that thing as the subject of what you're looking for. And remember, what are we looking for? We're looking for y as the subject. Kind of like when you solve normal equations. You want x is equal to some number, right? You don't just have the expression there all written out there. When you start solving it, we actually need that as the subject typically. The annoying thing though is that y is in the power here. Any ideas for what we can do? It's on log action. Yeah, great. Okay, so before we do that though, I may... Yeah, well, I don't like this negative here, so I'm actually going to get rid of that. And I have e to the negative y is equal to... Now, if you'd like, you can have x squared minus c. But again, like that c is just going to be a different constant anyway if you want. But you can leave it like that if you wanted. Cool. And then we're going to have... now, this is where I'll take the log of both sides. So we take ln of e to the negative y equals to ln of x squared minus c. And then, you know, you remember your power rules. So this is a power over here, so we can bring it down to the front. And this just divides through to become 1, simplifies to 1. And you can also multiply both sides by -1 here if you'd like. So y is equal to ln of x squared. Now, I think your answers here will probably have this though. Only because typically as a constant we add it on. And if you think about this situation here, the constant could just be a different constant. So they'll probably replace it at the end or something like that with like a k maybe or something like that. So just to emphasize, the constant that you use can change depending on what kind of operations you do. So just kind of be aware of that. And that's the general kind of solution to this, okay? There's your situation where I've got a general solution to my differential equation. That's with a constant there, okay? But now I want to find what we call a solution curve or a particular equation. And the way that that works is basically what we do is in the same sense we did with integration, we had some initial values, we substitute them in. We're going to do the same thing over here.
Wait, where did the minus go? And where did it go?
Sorry, the minus should be here.
Okay.
Yeah, so, sorry, good spot, James. So I multiply both sides by -1, that should be a negative as well. Sorry. Yeah, and typically, like, they just like to have, like, mathematical conventions, they like to add a constant on. So they prefer to have, like, a plus c or whatever, right? So in the general solution, if you look up answers for a question like this, they would probably have, like, plus c here. But, like, if you change what the constant should be, you should probably, like, change it at the end as well. Yeah, that's just, like, a notation thing rather than a strictly answer thing. I think this would have been fine here as well if you just multiply both sides by -1, right?
If there was a question in the exam,
Yeah.
would we get marked down if we didn't change the variable?
I think this is like one of the least things they could worry about. You could leave your answer here as negative C if you wanted as well. That's fine. Yeah. Questions about that one? Cool.